Hey everyone, and welcome to the Foundry by Forge College. Go ahead and grab your spot at the engineering drafting board because today's explainer is an exciting one. We're diving into designing real-time analysis and alerting for your Solana deployments. Now, if you've been following along with our track, in our previous lesson, we successfully set up our monitoring tools and we've got our system data flowing beautifully. But well, now it's time to actually build the tripwires. So let's just quickly look at the blueprint for today's explainer. We've got 5 structural steps we're going to take to build a perfect, noise-free alarm system. First, from metrics to signals. Second, the anatomy of an alert rule. Third, taming the alert noise. Fourth, a real-world Solana alert blueprint. And finally, we'll wrap up with the 4-phase alert workflow. Let's get straight to work.
Section 1. From metrics to signals. Making data actionable. Okay, so as I mentioned, in our last lesson, we started collecting just a ton of data from our Solana nodes. But what do we actually do with these continuous, never-ending streams of raw numbers? That's kind of the core problem here. You see, raw KPIs, things like RPC latency or transactions per second, they're just continuous numbers sitting completely passively on a dashboard. They don't do anything on their own. They might tell you a node is failing, sure, but only if you happen to be sitting there staring at the screen. On the flip side, we have actionable alerts. These are meaningful, discrete signals. Actionable alerts are what actually wake you up at 3 a.m. when your cluster is on fire.
Moving right along to Section 2, Anatomy of an Alert Rule, building the tripwires. To build an alert that actually works, we need to break down its structural anatomy. It really helps to treat it exactly like components on a technical schematic. Basically, there are 3 distinct dimensions to any alert rule. First up is the metric. This is what you are actually evaluating, like your RPC latency in milliseconds. Second is the aggregation window. This summarizes recent values, say taking a 30-second average. And this is incredibly important because it smooths out those weird transient blips that honestly don't really matter. Finally, we have the condition. This is the Boolean expression that triggers the alarm. For example, if the average is greater than 500 milliseconds for 2 consecutive windows, then boom, we have a breach.
Section 3. Taming the alert noise, avoiding alert fatigue.
Think about it like this. An alert system absolutely shouldn't be like one of those overly sensitive car alarms that goes off just because a leaf gently touched the windshield, right? If your system is crying wolf every 5 minutes, your operators are going to suffer from serious alert fatigue and just start ignoring it entirely. So how do we fix an overly sensitive alarm? Well, we do it by tweaking our aggregation windows and adding what we call refractory periods. Short aggregations, like 5 to 10 seconds, are incredibly fast, but they are very noisy. You're going to catch every tiny network hiccup. Long aggregations, like 1 to 5 minutes, are much better at smoothing out those transient network spikes, even if they delay your response time slightly. By balancing these windows, we filter out the noise so our operators can actually respond effectively when it counts. But what if you want the ultimate noise-canceling technique? Enter the composite condition. A composite condition is an alert rule that requires simultaneous violations across multiple, completely different metrics before it produces an alert. What this does is it encodes a known pattern of failure. It effectively proves that an issue is truly systemic across your infrastructure rather than just a single metric anomaly or a momentary glitch. It's a real game changer. Section 4, Solana Alert Blueprint. Let's look at a real-world example. Let's shift gears into the assembly phase. I want you to imagine you are actively monitoring a Solana cluster that supports a public RPC endpoint for wallet bridge traffic. Our first operational priority here is setting a warning rule to fire if the 30-second moving average for RPC latency exceeds 300 milliseconds for 2 consecutive intervals. Now, you might be wondering, why 2 intervals? Well, because it acts as a short refractory period to reduce flapping. We absolutely don't want to alert for a single 10-second spike, but we definitely do want to catch persistent latency regressions that are affecting our clients. Next, we stack the conditions for a composite critical alert. Look at these triggers together. A 30-second average RPC latency shooting over 500 milliseconds, coupled with a 2-minute decreasing TPS trend dropping below 600, and node CPU utilization spiking above 85% on multiple validators. When you combine latency, throughput degradation, and resource exhaustion like that, you guarantee you are looking at a true critical platform issue. There are no false positives here. That's just a real emergency. Finally, Section 5, Alert Workflow Phases, the quality assurance process. Now that we have our blueprint, we need a rigorous quality assurance process to put these rules into production without accidentally disrupting the entire system. We break this down into 4 phases: specify, implement, test, and tune.
And I should point out, these highly reliable methodologies are the exact same best practices taught across the advanced learning programs at Forge College. They're industry standard for a very good reason. Let's walk through them. Phase 1 is specify. Here, you draft a compact paragraph detailing the metric, aggregation, condition, severity, and the notification channel. But listen, the absolute most important part here is the runbook pointer. You must heavily emphasize including runbook links in your specifications. When an alarm triggers at midnight, your operators need exact step-by-step instructions to follow. Do not leave them guessing in the dark.
Phases 2 and 3 go hand in hand. Implement and test. Whether you use a declarative rule engine or an imperative script, you code the rule. But then you must simulate metric breaches. You can inject synthetic time series data. For example, explicitly stepping your simulated latency from 200 milliseconds up to 600 milliseconds. Why? To visually and technically ensure that the notification delivery channel actually works before a real crisis hits. You literally have to prove the alarm rings.
And finally, Phase 4, tune. You run your newly crafted rules against 24 hours of historical data. The goal here is simple. Count the false positives and adjust your parameters accordingly. Every single tweak you make must be justified by historical data. This tuning phase is what keeps the system perfectly quiet and out of your way until it is truly necessary to sound the alarm. Let's summarize the core mission of this explainer with a really defining quote directly from our source material. Real-time analysis reduces continuous KPI streams into discrete signals your operations team can act on. That right there is the ultimate sign-off on our blueprint today. We are taking the infinite noise of the blockchain and turning it into clear, decisive action. So, what is your immediate next step? Well, you need to implement and test 2 alert rules using what we've covered today. Once you've done that, you'll be completely ready to move on to our upcoming lesson, Automating Monitoring for Performance Optimization. That's where we'll learn to take these carefully crafted alerts and connect them directly to automated remediation pipelines. It's going to be fantastic. I'm going to leave you with this provocative question to ponder as we wrap up. Are your monitoring alerts actually actionable signals, or are they just an annoying car alarm that everyone on your team has learned to ignore? Think about your own setup. Thank you so much for joining me at the drafting board today. To learn more about this subject, dive deeper into Solana deployments, and discover other fascinating Web3 topics, I highly encourage you to visit forge.college. I'll see you all in the next explainer.